Actually, that may be best because I actually wanted to give a disclaimer up front before I get into this stuff. It gets really ugly, today's material. There are certain integrals versus 3 dimensions and 2 dimensions where there's a whole lot going on. It's not something that can easily be followed while it's being presented. It's something that you might need to revisit later. But I'll do my best to explain every step as I take it. But even then, I just go to absorb. So in other words, it's best to set lower expectations as to how well you will understand what happens when you leave this room, or stop watching this video for the first time. Okay, because all semester long, we have only dealt with PDEs that have one spatial variable and also time. For today, we're going to look at the wave equation on a 2 or 3 dimensional domain. So you have time and then x and y, or x, y, and z. The odd part is you would think that I would cover a 2-dimensional case first and then generalize that to 3D, but I'm actually going to go the other way around. I'm going to do 3D first and then reduce that to 2D. It's not a usual approach, but it works. Okay. So it turns out that when you use the right notation, expressing the solution to the wave equation in higher dimensions can be made surprisingly simple. It just takes a whole lot of work to get there and to come up with a notation that you need. So the problem that we're going to look at, so one thing that helps is at least we're not going to consider boundary conditions. We're looking at the wave equation in the entire space and only initial conditions to deal with. So here we have the wave equation in 3 dimensions and the customary initial conditions. For our first example, we'll assume that the initial displacement, the solution, is initially equal to 0, and then we'll just have a non-zero initial wave velocity. And then later, we'll look at the other way around. So it's easier to solve these 2 problems separately, and then for a general case, we can just add the solutions together. All right. Now, as refresh your memory, here we have a delta, actually an upside down delta, which is the gradient symbol squared times u, which, or delta u. So these mean the same thing. They both refer to the Laplacian, which technically is defined as the divergence of the gradient of u, which is where this notation comes from. That's just the sum of all the second partial derivatives of u that are with respect to the same variable twice. So uxx plus uyy in 2 dimensions, and then you add on u z in 3 dimensions. And we've always seen uxx in the case of just 1 dimension. Okay. Now, to solve this problem, since we're dealing with the entire space, we use a Fourier transform, which, again, we've only seen in 1 space dimension so far, but that definition of a Fourier transform readily generalizes to higher dimensions. Because in a 1-dimensional case, we have 1 over square root of 2 pi up front. So you just raise that to a power according to however many dimensions you have. So in general, it's 1 over the quantity 2 pi to the d over 2 power, where d is how many spatial dimensions you're in. So in this case, it's 1 over 2 pi to the 3 halves. And then inside the integral, before we would multiply your function you're transforming by e to the I omega x. Well, now we have your Fourier variable. This is a 3 component, so omega 1, omega 2, omega 3. So we have each one of these omegas multiplying one of the spatial variables. So omega 1x plus omega 2y plus omega 3 z. And then we integrate that over the whole space. Now, okay. I'm going to add in here I'm going to write out the general case just so you can see it more easily. And if I define omega to be a vector quantity in however many dimensions we have, so that's just u of omega, of vector omega and t. And we have 2 pi raised to the d over 2 power. Times the integral over all of rd for whatever d is. Okay. And then I can write the exponential as e to the minus I as a dot product of vectors. The vector omega, got a backslash there, dot product with a vector x. And I have recipe integral u of vector x t. And capital V is, or dv is a general volume element in whatever space you're integrating over. So it's helpful to write it this way because this looks very much like the one-dimensional Fourier transform we were working with several lessons ago. We just have to account for the spatial dimension here. So it's always e to the minus I dot product of a vector omega with a vector x. Just like in one dimension we had e to the minus omega x. So and then when we write this, when we specialize this to 3 dimensions, then we can write this way. When we take the Fourier transform of the PDE, then that works like it did in one dimension also. You take the Fourier transform of a time derivative, you just get the time derivative of a transform. So notice it's u hat tt. And you also remember when you take a Fourier transform of a second derivative with respect to x, you multiply by minus omega squared. Well, that's true here too. You multiply by minus and then each omega squared, they're all added together because it's a Laplacian. We have uxx plus uyy plus uzz. So the Fourier transform of uxx, we multiply by minus omega 1 squared. For uyy, we multiply by minus omega 2 squared. For uzz, we multiply by minus omega 3 squared. All those are added up, and our coefficient c squared is still sitting there. So this is the ODE that comes out of it. All right. And I can write this in a more compact form also. By keeping in mind, here we have a sum of squares. That can be thought of as the magnitude of a vector squared. So I can write that as the magnitude of omega, the vector squared. I'll define that here. Squared plus omega 2 squared plus omega 3 squared. Okay. So again, now that way the ODE looks much more like the ODE that we had in the one-dimensional case. So you can see how it generalizes from one dimension to several dimensions. These are initial conditions. We take the original initial conditions. We just take the Fourier transform of those. So we'll have 0 for the first one, and then the Fourier transform of psi for the second one. And that leads us to this initial condition here. Pretty questions up to this point. I wonder if anybody thought that when I announced on Monday that there would be no class next Wednesday, that they somehow thought I was referring to this Wednesday. Oh well. Right. So now we go about solving this ODE with these initial conditions. And this turns out to be a solution that's, okay. So it turns out to be 1 over c magnitude of omega times the Fourier transform of the second initial condition times sine of c omega t. Now, I want to take a little time to explain how I got this solution. Because if you look at this ODE, I've written it slightly differently here. So we have u hat tt is minus this coefficient squared times u hat. Anytime you have a second derivative equal to your solution times minus a constant squared, that should tell you that your solution is a combination of a sine and cosine. Because, for instance, if you have a function sine kx, you take the second derivative, what do you get? Minus k squared sine kx. Same thing if you have a cosine. So anytime you see that situation, this kind of ODE, second derivative is equal to minus a constant squared times your solution, then you can jump directly to here and get your general solution. It's some constant times a cosine of whatever is being squared times your variable, in this case t. And then similarly you have a sine term involving the same coefficient. Then you have to use the initial conditions to get the values of C1 and C2. So for example, if I set t equals 0, the sine term will go away, the cosine will become 1, and I'm left with just C1. But for this problem, that's supposed to be 0. So that's how you know that there's no cosine term. On the other hand, if I take a derivative of this with respect to time, this cosine becomes a sine. Now go away when t equals 0. This sine becomes a cosine, but we're going to get a factor of c omega out front. And the result has to be equated to this initial value. That's why we end up dividing by this c omega here. Now, is there any questions about how this solution was arrived at? Or at least that's the Fourier transform of our solution. We still have to take the inverse transform. So how does that go? We start that here. So, actually, to explain what I'm going to do before I really get into it. Okay, I'm going to write this a little differently. I'm going to put this factor and then the sine together. And I'm going to put part of this in parentheses. Okay. So here we have our Fourier transform being the product of these two. And you may recall from back around lesson 10, 11, 12, when I first talked about Fourier transform, the product of a Fourier transform corresponds to the convolution of the original functions. So if I were to take the inverse transforms of these pieces, these two pieces individually, then that helps me because instead of multiplying the inverse transforms together, I would take their convolution. So because of the Fourier transform is a product, I know that the inverse transform of this whole thing is a convolution of the inverse transform of this with the inverse transform of this. Now, the inverse transform of this I already know. It's just psi of xyz. So that part is trivial. But then I still need to work out the inverse transform of this to take the convolution of it with psi of xyz. So that's what I'm going to do now. Is work out the inverse transform of the sine c omega t over c omega. And that's where things begin to get really ugly, as you can see. But I'll walk you through it. So here we have, this is just what the definition of a 3D inverse Fourier transform gives you. And it's similar to what you just saw, except now there's no minus. Now, what I'm going to do to try to evaluate this integral is express everything in spherical coordinates, which you would have seen in Math 280, multivariable calculus, and you might not have seen since then. Okay, so how do I go about doing that? So, all right. Okay, I need to define some notation here. Okay. So I need to define rho, which is our radial variable in spherical coordinates. That will be the magnitude of omega. So keep in mind, my integral is over all of three-dimensional space, but it's omega 1, omega 2, omega 3 space, not xyz. xyz, for purpose of this integral, is thought of as a constant point. So rho, so where we see rho, that refers to not the magnitude of xyz, it's the magnitude of omega 1, omega 2, omega 3. So that's how we get sine c rho t. So any place where you see magnitude of omega, that's just rho. So that explains where this fraction comes from. Rho squared sine phi is the Jacobian of the change of variable from Cartesian coordinates to spherical coordinates that you might remember. For example, when you go from Cartesian to polar coordinates, you have a factor of r in there. It's that. This is a corresponding thing for spherical coordinates. You have d rho, d phi, d theta. Here we have when this is expressed in spherical coordinates for omega 1, omega 2, omega 3, and r is the magnitude of in Cartesian coordinates. So r is the square root of x squared plus y squared plus z squared. That's where, so this exponential, when converted to spherical coordinates, becomes this. Okay. Now, okay, yeah, so actually, let's explain that here, but one other explanation I have to give is that it's not just standard spherical coordinates. In regular spherical coordinates, the north pole, phi equals 0, points in a direction, it points straight up. So in the direction of vector 0, 0, 1. Here, the north pole is oriented to x, y, z. So it's a rotated or skewed spherical coordinates. That is why, that's a justification for why this simplifies to this. So that non-standard orientation gives me a simpler expression here. Okay, because rho cosine phi, that's how you express your third coordinate, your z, in spherical coordinates. So by having my spherical coordinates oriented so that 0, 0, r corresponds to this direction, then that's what lets me simplify this all the way down to here. And so it's a bit odd, but it helps later on. Okay. So now I want to try to proceed with the integration. So first, nothing in here depends on theta. So I could take all of this and work on it separately, and then I have that times the integral from 0 to 2 pi of 1 d theta, which would just give me 2 pi. So the integral of theta part will just give me a factor of 2 pi, which would sit out here, and that's what causes this to simplify to square root of 2 pi down below. C is a constant, pull that out, so it's sitting here. Now, anything that doesn't depend on phi, I can pull out to this point. So I have rho squared over rho becomes rho. I have sine c rho t, so all that sits out here. And then this part depends on phi, so it has to stay in the innermost integral. So now I can focus on evaluating this. But what works out nicely about this is I can make a u substitution. U is equal to cosine phi. So then du is minus sine phi d phi, which is sitting right here. So I make that u substitution in this integral, gives me this. But now this is an ordinary exponential. I can just go ahead and evaluate this. Okay. And, okay, really it's this innermost integral that I'm evaluating here from minus 1 to 1. Now, one thing I want to point out is that when I integrate this, notice I have e to the I r rho u, integrating with respect to u. Well, then I have to divide by I r rho. Well, you see I have I r down here, but I also have a rho sitting up here. That's going to get canceled. And now I've plugged in the limits, minus 1 and minus 1. That gives me this. But this is equal to 2i sine of r times rho. And so the I from that's going to cancel with the I down here. That helps keep everything real. And then that's with the constant factor sum. So now I have this. So now I have one integral left to evaluate with respect to rho. A product of signs is difficult to evaluate by itself. I rewrite it as using a product to sum formula. That gives me cosines that I can evaluate. But this actually turns out to be, so this integral works out to be from 0 to infinity, the Dirac delta function, evaluated at r minus ct. So, so that worked out beautifully at least. So now, I've completed the inverse Fourier transform of this part of my Fourier transform of my solution. So now I can express the solution of my original problem, u of x, y, z, t, as the convolution of my initial data with Fourier transform I got earlier. Okay. Now I have to be careful with notation. You recall with convolution, you have a function of your variables you're integrating with respect to, and then what goes here is a function of these variables minus these variables. And you don't see that here, but that's because it's worked into the definition of R prime. You see, R prime is defined to be this. It's the magnitude of the difference between your x, y, z and your x prime, y prime, z prime. So that's how you tell that this whole thing is a convolution. So now I need to evaluate this integral. Again, most easily done in spherical coordinates. So when I express everything in spherical coordinates, okay, so here I have where the origin is considered to be at x, y, z. So x prime is this. This is y prime. This is z prime. So that's my spherical coordinate system. Again, a bit different from a standard one. Okay. Here's my Jacobian from a change of spherical coordinates. Rho corresponds to, that's the magnitude of the difference between x, y, z and x prime, y prime, z prime. Okay. So R prime and rho are the same thing in this case. They're very equal. Okay. So now, as far as evaluating this, I need to. I have some constant factors that I can pull out. Here I have also from a delta function. This is equal to 0 unless the argument is 0. So rho is equal to ct. So that is how this rho squared becomes this ct squared down here. And then the integral with respect to rho goes away. All right. This part is still here. And what ends up happening is, okay, the c squareds will cancel. I have t squared here, t down here, so that leaves me with t. And then, aside from that factor of t, what's left? It's the integral of psi on over the sphere. So not the interior, just the boundary of the sphere of radius of radius c times t. And what we have out here, after I cancel the c squareds and I set the t aside, I end up with the surface area of the sphere. Okay, hold on. Oh, sorry. I apologize. I need to backtrack a little bit. I don't actually cancel the c squares. I have to leave this here. If I multiply this fraction by t and divide by t, I have 4 pi ct quantity squared in the denominator. That's the surface area of this sphere of radius ct and center x, y, z. when I integrate a function over a sphere and divide by the surface area of the sphere, that's average value of a function on the sphere. So that's what the bar means. And we see it written out here, the definition of psi bar. Average value of a function defined on a sphere. So you're going to call it calculus 2, you integrate a function from a to b, and you divide by b minus a. You're integrating a function over an interval, you divide by the length of the interval. That's average value of one dimension. In general, when you're integrating a function over a certain domain, and you divide by the size of that domain, whether it's length, area, length of one dimension, area 2 dimensions, volume in 3 dimensions, that's average value of a function over that domain. The CT squared has to stay here because that's part of that comes from a change in spherical coordinates. And since this is not quite the surface area, I just have to multiply and divide by t to make this part of the surface area, and then I have this factor of t sitting here. All right. So while I could cancel the c squares, that doesn't really help me because I want to have a nice compact representation of what this integral means. And by not canceling the c squares, making this fraction up front be 1 over the surface area, it allows me to recognize, oh, what I have here is the average value times t. So now I can express my solution in an extremely compact form. Right. What do you this will be on? No, we're not even done yet. So, with questions about what we have here? Yes?
How did you get the 4 pi c squared times t, like as a denominator?
Okay. So, from this point, okay, so I have, all right, so I have 2 pi to the 3/2 and 2 pi to the 1/2, so that gives me 2 pi quantity squared. Okay, so then I have 4 pi squared at this point, but then I have this pi here. So now I have, so that's where the 1 over 4 pi comes from. And then, as for the c squared, okay. Right. Okay, so I got this c sitting here already, but because of the delta function being 0, unless rho is equal to ct, this rho becomes ct. So now I have c times t.
Okay. So would the Dirac delta function just be equal to 0, or?
Yeah, delta function is a rather odd duck. In fact, it's not even a function; it's a distribution. What we're saying here is that because we're integrating, if you consider the integral with respect to from rho going from 0 to infinity, that of the delta function ends up being equal to the value of the integrand, the whole integrand, at the argument which makes this 0. And that leads to rho being replaced with ct throughout this whole thing.
Okay.
And then the integral goes away. All right. Other questions?
What's the R prime again? Just you saying that this is what?
Oh, okay. So since I'm integrating over all of free space, and my x prime, y prime, z prime are my original variables of integration, that Okay. This part in the square brackets has to be a function of x minus x prime, y minus y prime, z minus z prime, because it's a convolution. So, and because from this formula, r is the magnitude of that vector argument, in this case, I define r to be that magnitude. Just so I can express this more compactly. You have a question? Okay, so all of that work to get extremely simple solution formula. Now we go the other way. This part of the initial data is non-zero, this part is zero. Thankfully, a lot less work because of what we've already seen. We can rely on that. Because, suppose I go back to the previous problem. So this is the equation I was solving earlier where we have non-zero initial data here, but here whatever initial data I have here, I'm now putting here. Well, this, I know what the solution to this is because I just did it. It's this. Now, suppose I consider the derivative of this with respect to t. So, I know that v satisfies this PDE. So now I take the derivative of both sides of this with respect to t. Okay. So that gives me this. If I just differentiate both sides of this with respect to t. But I can write this time derivative this way. I can group the time derivatives however I want. Similarly here, I can move this differentiation in respect to time past the c squared, past the spatial differentiation happening here, and I have c squared times Laplacian of dv dt. So this side equals this. This is equal to this, just by rewriting how differentiation is done. So now, just as v satisfies the wave equation, dv dt also satisfies the wave equation. But then, knowing that v satisfies v's initial conditions, what initial conditions does vt satisfy? Well, here I have vt at t equals 0 satisfies this. Well, so that I just write that down here, same thing. Then I look at its time derivative. What is it equal to at t equals 0? Well, okay, I need to do a little extra work here to show you. The product rule for a second derivative. Because v is equal to t times the average value of phi. And I would use this as, I could apply the product rule twice, but it's helpful to know what the rule is for second derivative directly. So that would be t double prime times the average of phi plus 2 times the first derivative of t times the first derivative of the average of phi, plus t not differentiated at all times Okay. Now, so now if I want to simplify this, well, the second derivative of t is 0. First derivative of t is 1. So now when I go to simplify this, I can take that into account. That's 1. Okay. And okay. But now what happens? Well, now I have to evaluate this at t equals 0. Well, that's going to cause this to go away. The only term that's left is the average value of phi evaluated at okay. But actually, what I can do is okay, that's the same as the average value of phi t. Okay, but phi is not a function of t; it's a function of x, y, and z. So that's why all of this turns out to be 0. So, what do I have here? dv dt satisfies the wave equation. dv dt at t equals 0 is equal to phi. The derivative of dv dt at t equals 0 is 0. In other words, dv dt is the solution of this problem. So u equals dv dt. So now that I know the solutions of this problem and this problem, or the other part of initial data 0, I can add those two solutions together to cover general initial data. That's what I do here. So now I have wave equation, u is equal to phi, du dt is equal to psi, and here's my solution. This comes from the first problem I worked out. And then to cover this part of initial data, it's that solution, but I take a derivative with respect to t. And this is called Kirchhoff's formula. It's also known as Poisson's formula depending on the context. All right. So questions about how this formula got put together from the previous work? Now, there's an interesting interpretation of this solution formula because we're dealing with the average value of the initial data over a sphere. And keep in mind, it's just the bounding sphere, the shell, not the inner part of it. So let's suppose the initial data is 0, except within a small ball. So then what happens is, because keep in mind, we're taking the average of these over a sphere where the center is at x, y, z, and the radius is c times t. So let's suppose if the initial data is 0, except within some small sphere, for instance. Well, we're going to look at the overlap between that sphere where the initial data is non-zero and a sphere with this center and radius ct. If those spheres do not overlap, then the solution is 0 at that point. So if this point, x, y, z, is far away from where the initial data is non-zero, the solution will be 0 at this point for quite some time. That will only change when t is large enough so that the radius of this sphere, ct, intersects with whatever sphere in which the initial data are non-zero. So, in other words, the solution exhibits what's called a sharp leading edge. That the solution is at a certain point, if you're just observing what's happening at that one point, it's 0, 0, 0, 0. Eventually, bam, something pops up. And you have some non-zero data. Then, the sphere that you're using to evaluate the solution at this point, as radius ct, as t increases further, eventually that sphere will be so large that it will swallow whole the sphere where this is non-zero. But the point is it won't intersect anymore. So the solution will go back to being 0. That's called a sharp trailing edge. So if you're observing a solution at any selected point, you'll see that 0, 0, 0, eventually it's non-zero for a slice of time, and then it goes back to being 0 again. So that's how solutions of a wave equation behave in 3 dimensions. And this is called Huygens principle, which is proven to be satisfied in any odd dimension starting from 3. So it's not true in 1 dimension. And we can see that from D'Alembert's solution formula that involves the integral of the initial velocity, g, from x minus ct to x plus ct. So there's no possibility for a sharp leading edge or trailing edge in 1-dimensional case. But for any odd dimensions beyond that, this is how solutions of the wave equation behave. And it's all because these average values only consider the boundary of the sphere, not the interior. Any questions about this interpretation?
So it only holds in odd dimensions, or?
Yes.
Okay.
Yeah, and I'm about to show you why, at least in 2-dimensional case, it does not hold. All right. So what happens in 2 dimensions? So here's our problem in this case. Now, so we're going to use a 3-dimensional solution in the case where initial data depends only on x and y, not a function of z, because that dimension has to be thrown out. So, same appearance, just psi is now a function of x and y. So I can use the 3-dimensional solution formula that would give me this. It's just that this part is irrelevant because phi is only a function of 2 variables. So in fact, I could just delete this right now. Or I should. Okay. But this is it's still expressed in spherical coordinates. So this is an integral over a 3-dimensional entity, just that we only have the x and y parts plugged into psi. Now, but the thing is, this isn't really practical because now we're expressing the solution of a problem defined in 2 dimensions with a 3-dimensional integral. We like to express this integral as being over a 2-dimensional entity. So instead of working with a sphere of radius ct, we think in terms of a disk of radius ct. And so by disk, I'm referring to not just a circle, but the interior also. And the way that we get this integral from being over a sphere to over a disk is called the method of descent. And geometrically, you can think of it as stemming from the fact that if you consider the top half of a sphere, you can think of each point on that sphere as being in a one-to-one correspondence with points on the disk that sits at the equator. By basically projecting a point on the sphere along the z-axis down to the xy plane. So literally there's a descent going on, and the point is sitting on the sphere, or just moving it down to x equals 0. But we need to do it in such a way as to figure out what this integral would look like if being over a disk. So there's a change of variable going on here. So we need to, because look at our variables here, we have d phi and d theta. So those are two of the three spherical coordinates. We want to work with polar coordinates, r and theta. Now, the theta in spherical and polar coordinates are the same. We need to express this angle, the angle of inclination, phi, in terms of the polar coordinate variable r. So how can we do that? Well, on a sphere of radius ct, the z-coordinate in spherical coordinates is z is equal to a radius times cosine of phi. So all I've done here is I've rearranged this to isolate phi. And if I keep in mind that in polar coordinates, r is equal to, dang it, square root of x squared plus y squared. So, but the thing is, x squared plus y squared plus z squared is equal to ct squared. So I can use this to express z. So now I've eliminated z. So now I have this expression for phi. So now I want to rewrite d phi from the integral, because this, really what I'm doing is, I'm making a u substitution. Wherever we see phi, I'm going to replace phi with this. That brings me to polar coordinates. But now I have to work out what d phi is. Well, this part here, this first fraction, comes from the formula from a derivative of arc cosine, and then from the chain rule. So from a chain rule, I get all of this. And then I simplify this as much as I can, kind of a pain, and this is what I get for my u substitution. Then, from the other formulas for spherical coordinates, like x is equal to ct sine phi cosine theta, and similarly y is equal to ct sine phi sine theta, and x squared plus y squared equals r squared. So I put these three formulas together. So in fact, if I take x squared plus y squared, from cosine squared plus sine squared equals 1, I get r squared is ct squared sine squared phi. So I have this relationship that lets me express this sine phi in terms of polar coordinates. So I've dealt with the d phi from a u substitution. Now I have a way to deal with this too. So now, here's my original integral. And now I can rewrite it in terms of polar coordinates. So wherever we see ct sine phi, that becomes r, here and here. From the d phi, that's where this square root comes from. Sine phi, here the integral becomes r over ct. Okay. And for the u substitution, phi went from 0 to pi in spherical coordinates. But in this change of variable, so right here, when phi is equal to 0, then this this value has to be 1, which would happen when r equals 0. When phi is equal to pi over 2, this has to be 0, so r equals ct. So that's how the limits of this integral from 0 to pi in phi becomes 0 to ct in r. So now we have this integral in polar coordinates to evaluate. So now, based on what I had before from Kirchhoff's formula, I can express my solution of a general two-dimensional wave equation in terms of these integrals. This one from the second part of initial data, and then a time derivative of the same kind of integral formula involving the first part of the initial data. But if you look at what's happening with these integrals, this is an integral over the entire disk, r going from the center of the disk out to the edge, and then all angles 0 to pi and theta. Because it's covering the whole disk, the interior of the circle, unlike the three-dimensional case where it was just over the boundary sphere, Huygens principle does not hold in 2 dimensions. So we do not get a sharp leading edge or sharp trailing edge in this case. So another way of putting it is, if we're evaluating the solution, let's suppose the initial data is 0 almost everywhere. If the point xy is far away from where the initial data is non-zero, then yeah, first the solution at xy will be 0. Then, as t gets larger and larger, we look for the intersection of the disk centered at xy, radius ct, with the disk in which the initial data is non-zero. Once those disks overlap, then the solution will, at this point, will be non-zero. But then as t continues, this disk gets larger and larger. It will always contain the disk where the initial data is non-zero. In other words, it will remain non-zero forever. Unlike 3 dimensions where it's non-zero for a period of time and then it goes back to being 0. So this one happens in an even number of dimensions. Okay. So questions about what happened here? They're probably fried your brains by now. Or are there homework questions? All right, I guess I'll do it.
You
Oh, wait.
said class is canceled next Wednesday, right?
Right, yeah, it's a week from today.